This is Module 5, Number Systems, of the Cisco Academy Introduction to Network 7.0 curriculum. The binary number system is the most commonly used in all electronic devices because it only has two digits, either a 0 or a 1, which could also be related to high or low, yes, no, on, or off. All numbers can be represented in the binary number system. We just need to become familiar with how the binary number system works. So as stated earlier, the binary numbering system consists of ones and zeros. Each one is called a bit. The decimal numbering system consists of digits 0 through 9. As you may recall, the base of a number system indicates how many distinct digits are in that number system. Decimal, being 10, has distinct digits 0 through 9, while binary, being 2, has distinct digits 0 and 1. All hosts, servers, and network equipment using binary addressing to identify each other. Each address is made up of a string of 32 bits for an IPv4 address, or 128 bits for a IPv6 address. For an IPv4 address, the string of 32 bits is divided into 4 sections, each section referred to as an octet. Because it's 4, 32 divided by 4 is equal to 8, or an octet. Each octet contains 8 bits, or more commonly referred to as 1 byte, separated by a dot. For ease of use by people, this system, referred to as dotted notation or dotted decimal notation. Decimal notation should be familiar to all in this class. Working to the left of the decimal point, or otherwise known as a radix point, you have the base of the number system 10 first to the 0 power. Anything to the 0 power has a decimal weight of 1. To the left of that is 10 to the first, or 10, 10 to the second, or 100, 10 to the third, or 1000. Therefore, a number such as 5,432 base 10 is 5 times 10 to the third, or 5 times 1000, 4 times 10 to the second, or 4 times 100, 3 times 10 to the first, or 3 times 10, and 2 times 10 to the 0, or 2 times 1. In binary, the base is 2. Therefore, we start with a binary point, or for simplification, it can be referred to as a radix point. Working to the left, we have 2 to the 0 power, which, as stated earlier, anything to the 0 power has a decimal weight of 1. 2 to the first, or 2. 2 to the second, or 4. 2 to the third, or 8. 2 to the fourth, or 16. 2 to the fifth, or 32. 2 to the sixth, or 64. 2 to the seventh, or 128. 2 to the eighth, or 256. 2 to the ninth, 512. 2 to the 10th, 1024. If we continue on, 2 to the 15th is 65,536. 2 to the 10th, or 1024, is equal to 1K. In networking, as in computer systems, 1K is not 1000. It is 1024. 2 to the 15th 65,536 is therefore equal to 64K. The Commodore 64 computer was named 64 because it has 64K of memory. If I wanted to convert a binary number or a decimal number into binary, such as 132, it would be 1 times 128 plus 1 times 4, giving us a binary number of 1, 0, 0, 0, 0, 1, 0, 0. There are multiple ways to convert a decimal number into binary, as we will see in the next slide. The first method, a double-dabble method, works by repeated division. We take the decimal number, in this case 177, and we divide by 2. That gives us 88 with a remainder of 1, which we put to the side. We then divide the 88 by 2, which gives us 44, and it went in evenly, so the remainder is 0. We divide the 44 by 2, 22, with a remainder of 0. We divide the 22 by 2, 11, with a remainder of 0. We divide the 11 by 2, 5, with a remainder of 1. We divide the 5 by 2. Answer is 2, with a remainder of 1. We divide the 2 by 2. Goes into it 1 time, remainder of 0. And we try to divide the 1 by 2, which we cannot do. So it's 0 times and a remainder of 1. Once we have the remainders, we let that column fall to the right. And we have the binary representation for 177. In this case, 1, 0, 1, 1, 0, 0, 0, 1. The second method uses the weights, the positional weights in powers of 2. 1, 2, 4, 8, 16, 32, 64, and 128. The next position would be 256, which is obviously greater than our 177. We then work this very similar to a checkbook. I have 177. Can I subtract 128? Yes, I can. It leaves me with 49. I cannot take 64 away from 49, so that column receives a 0. I can take 32 away, so that column receives a 1, and it leaves me a remainder of 17. I can subtract 16 from that, so again the 16s column will have a 1. 16 from 17 leaves me 1, so I cannot subtract 8, 4, or 2, so those 3 columns receive a 0. The final column is a 1, so I can take 1 away from the 1, which leaves me a final result of 0. And you will see in the colored blocks, both answers are exactly the same. 1, 0, 1, 1, 0, 0, 1. Now, using the double-dabble method, you had to take 8 distinct steps to get to the answer. Whereas with the subtraction method, you only had 4 steps. In 8 steps, the possibility of making a mistake is twice that of the 4 steps. Either method works, but in the double-dabble method, even if the remainder is a 0, you are still doing a mathematical operation, which you do not do in the subtraction method. Therefore, usually the subtraction method is much more accurate. As we see with our positional weights here, the positional notation means that a digit represents different values depending on the position the digit occupies in the sequence of numbers. The decimal positional notation system operates as shown. And as the chart is showing, 10 to the third is 1,000, 10 to the second is 100, 10 to the first is 10, 10 to the 0 power is 1. This is just another way of laying out what was done in the previous slide. Binary, as shown in the previous slides, you have a positional value of 2 to the 0. In this case, we end at 2 to the 7th. It gives us 8 binary digits, which is the most common in IPv4 addresses. To convert a number, we can take their positional value, 128 and 64, the only two columns where there is a 1, add those two together, and we end up with a result of 192. Using a positional weighting method, we can very easily convert from binary to decimal or from decimal back to binary. Here are some examples going into an IP address. An IP address made up of 4 octets as shown on the right. The first octet being 192, which is 128 and 64 is equal to 192. The second octet, 168. We have 128 plus 32. Added together, that would give us 160. I add 8 more, and it gives me 168. The next column, or the next octet, is 11. So if we take a look, because it is an octet, we need to put in the leading zeros to make it 8 binary digits long, 1 byte. And we have 8, and 2 is 10, and 1 is 11. When looking at binary numbers, odd binary numbers will always have a 1 in the first position. Even binary numbers will always have a 0 in the first position. The last, we have 8, and 2 is simply 10. So as you can see, we can convert this long binary number to a simplified dotted decimal notation for ease of our use. The computer system or the network still uses the binary value. The binary positional value table is useful in converting a dotted decimal IPv4 address to binary. You want to start in the highest position value, the most significant bit. And is this the decimal number of the octet n equal to or greater than 128? If it is greater than 128, we would put a 1 in that box and move to the next. If it is not greater than 128, we would put a 0 in the box and move to the right. So if yes, record a binary 1 in the 128, subtract 128 from the decimal number, and move to the 64 positional value. You repeat those steps, continuously moving to the right until you've gotten to the 1, at which time your decimal number should have been converted to a binary number. Here is an example to convert 168. Starting with 168, if I subtract 128, I would end up with a remainder of 40. Since I was able to subtract 128, I put a 1 in the 128 column. My next column is 64, which I cannot subtract from 40. So I put a 0. The next column is 32, which I can subtract from 40. So I put a 1 in that column, I subtract it from 40, and it leaves me a remainder of 8. I cannot subtract the 16, so that becomes a 0. I can subtract the 8, so that column becomes a 1. And I subtract 8 from my 8, leaving me with a remainder of 0. So all remaining bits to the right are now zeros. Routers and computers only understand the binary. Humans work in the decimal. And it is important for you to gain a thorough understanding of these two numbering systems and how they are used in networking. We use the dotted decimal system for ease of our use, while the computer system still uses the binary. You can imagine the confusion that would result if we tried to tell somebody an address by the binary, such as instead of saying 192.168.10.10, we would have to say it is 11000000101001, and so on. You can see the confusion that would result. We can also use Excel to convert binary into a decimal value. I put an example here of first how to convert. The value of the box of A2 is multiplied by the power, 128. We then add that to the value in the box of B2 times 64, C2 times 32, D2 times 16, E2 times 8, F2 times 4, G2 times 2, and H2. There is no reason to multiply H2 by the value in H1 because that is a 1. In Excel, all formulas begin with the equal sign. Sum is telling us to add up these values. Once I have gotten the value, as we see in column I can add those into a sentence if I so desire. Again, in Excel, if I'm going to start a formula, I need to start with the equal sign. Because I'm entering text, I would open my quotations, type the text, including any spaces, close the text, then use the and sign and what box to then insert. And as we can see, the 0 at the end is what we calculated. The last case, 255, is what we calculated. Very easy to create an Excel sheet to work with IPv4 addresses. The other addressing system, or the other numbering system, I should say, that we use is the hexadecimal numbering system. MAC addresses and IPv6 addresses use hexadecimal. Hexadecimal has a base of 16. So, as we see here, to understand the IPv6 addresses, you must be able to convert hexadecimal to decimal and vice versa. Hexadecimal is a base 16 numbering system using the digits 0 through 9 and then letters A through F. So A is equivalent to 10, B is equivalent to 11, C is equivalent to 12, D is equivalent to 13, E is equivalent to 14, and F is equivalent to 15. It is much easier to express a value as a single hexadecimal digit than as 4 binary digits. As you may have noticed, and is indicated by the slide, as the base of a numbering system goes up or increases, you need less digits to represent a number, such as 1110 in binary, comprised of 4 digits, is equal to 14 in decimal, comprised of 2 digits, equal to E in hexadecimal, comprised of 1 digit. To create a hexadecimal chart, it is very easy if you understand first the binary. Here we can see I have 4 columns, 1, 2, 4, and 8. The positional weights of the first 4 columns in a binary number. I start at the most significant digit, and I put 8 zeros, followed by 8 ones. I only do 1 rotation. This gives me an ending point, so I know how far I need to go for the maximum amount of combinations. Starting at the ones, we would not know precisely where to end. We then proceed to the next column. 4 zeros, followed by 4 ones, followed by 4 zeros, followed by 4 ones. And the first column with the 8s already established our ending point, so we stop there. Going to the next column, 2, we go with 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros, and 2 ones. And again, we know where to stop by our original column of 8. The final column, the ones, is just a sequence of 0 and 1s until we get to the end. Now, putting that into this second table, I've taken out all except the binary columns, the 1 to the 4 and the 8. And as we can see, we have the binary counting up from 0 through 15 in order, representing our hexadecimal numbering system. This is the easiest way I have found over the years to establish a hexadecimal conversion chart for people that are not necessarily yet familiar with binary and hexadecimal. We see here an IPv6 address is comprised of 128 bits in length. Every 4 bits represents a single hexadecimal digit. So if we divided 128 by 4, we would get 32 hexadecimal digits in an IPv6 address. They are separated into groups of 4 and separated by a colon. Each group could go from the lowest being all zeros to all Fs being the highest. Each group will have 16 binary digits, ones or zeros. Each 4 hexadecimal character group is referred to as a hextet. You may recall in an IPv4, because it had 8 digits or 8 binary digits in it, it was referred to as an octet. Here, because each grouping has 16, it's referred to as a hextet. We have to be able to convert from decimal to binary to hex. First, we divide the binary string into groups of 4, starting from the rightmost position. This is normally referred to as chunking, in that just like eating a large steak, you cut it into smaller chunks for easier management and consumption. We convert each of the 4 binary numbers into their equivalent hexadecimal digits. In this example, 168 converted into hex using a 3-step process. 168 in binary is 10101000. If we divide this number into 2 groups of 4, starting at the binary point or radix point, we read each group as if it was 8, 4, 2, and 1. So 8 and 2 is 10, or in hexadecimal A. 1 and all zeros is an 8, which is 8 in hexadecimal, so it is equivalent to A8. We can also convert hexadecimal to decimal. It is much easier to go to a binary as the first stop. So first we want to convert the hexadecimal number to 4-bit binary strings. We create the 8-bit binary grouping starting from the rightmost position and convert each 8-bit binary grouping into their equivalent decimal digit. In this example, D2 is converted. D is equal to 13. If you recall, A is 10, B is 11, C is 12, D is 13. 13 in binary is 8, 4, and 1, or 1, 1, 0, 1. 2 in binary, being a group of 4, we must have the leading zeros, is 0, 0, 1, 0. When we put those together, we get an 8-bit grouping of 1, 1, 0, 1, 0, 0, 1, 0. If we then convert that grouping, in the first position we have 128. The second position we have 64. We do not have the 32, but we have 16. We do not have 8, we do not have 4, but we have 2. And we do not have a 1s. So if we add this up, 8 and 4 is 12, 6 is 18, and 2 is 20. Writing the 0, carrying the 2. 2, 4, 10, and 1 is 11. 1 and 1 is 2. 210 in decimal. So as you can see, we can go from decimal to binary to hex, or hex to binary to decimal, binary directly to hex, or binary directly to decimal. If I'm converting directly from decimal to hex, the process is much more complex. It uses the same methods, but because the numbers are bigger, it makes it a little bit more difficult. Here, we can see our hexadecimal notation. 16 to the 0 power has a decimal weight of 1. 16 to the first, decimal weight of 16. 16 to the second has a decimal weight of 256. 16 to the second, 4096. In this example, as I used above, 5432. If I subtract 4096 from 5432, it would go into it only one time, and it would give me a remainder of 1336. I would then divide the 1336 by the 256, giving me 5 and a remainder of 56. I can divide the 56 by 16. It goes into it 3 times with a remainder of 8. I divide the 8 by 1, giving me 8, remainder of 0. So in hexadecimal, 5432 base 10 is equal to 1538 base 16. And as you can see, this is just another example of how, as the base of a number system increases, the size of the number decreases. As was discussed on the previous pages, but in a little bit more laid out fashion, here I took my 5432 and I converted it into binary. 4096 plus 1024 plus 256 plus 32, 16, and 8 adds up to 5432. Then I read each group of 4, so I separated, starting at the radix point, each group of 4, 1, 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, and I have to put in my leading zeros, or 0, 0, 0, 1. It does not change the value of a number to put in leading zeros, only trailing zeros. And as we can see, reading each group, 0001 is 1, 0101 is 5, 0011 is 3, 1000 is 8. So we've converted from a decimal to a binary to a hex. Both systems work, as we saw on the previous slide. The system works just as well. But it is much easier using this method. That concludes Module 5, dealing with number systems. You must become proficient with these number systems, and the only way to do that is to practice converting numbers from decimal to binary to hex, from hex to decimal, or from hex to binary to decimal. Do this many, many times to become totally proficient with these number systems.